This leads scientists to explore the concept of xenobiology, life that is truly alien in form, function, and biochemistry. Such life might not leave the same biosignatures we look for on Earth. It may not breathe oxygen or photosynthesize or even resemble anything we might call a cell. It could be microbial or macroscopic, solitary or networked. It could emerge in oceans, under ice, or deep within a planet's crust. That's why astrobiologists urge caution. When looking for life on exoplanets or distant moons, we must avoid Earth-centric biases. A planet with no oxygen in its atmosphere might still host anaerobic microbes. A barren surface may hide a subsurface biosphere. Life could be hidden, quiet, or fundamentally unfamiliar. SETI, the search for extraterrestrial intelligence, takes a different approach, scanning the sky for technosignatures, radio signals, laser pulses, or patterns of light that cannot be explained by natural processes. So far, SETI has not found definitive proof of intelligent life, but the search is ongoing and expanding into new wavelengths and techniques. Recent discoveries have also led scientists to ask, are we looking in the right places? Should we focus more on moons than planets, on subsurface oceans rather than atmospheres? Could life be hiding in plain sight, using forms or behaviors so alien we fail to recognize them? At Infinity Beyond, we believe that the universe is far too vast and complex for Earth to be the only cradle of life. With hundreds of billions of stars in the Milky Way, and likely trillions of planets, the odds favor life. Perhaps not intelligent, perhaps not familiar, but life nonetheless. And when we finally find it, whether through a telescope, a probe, or a whisper from the stars, it will redefine our understanding of biology, our place in the cosmos, and what it truly means to be alive. As we peer deeper into space and uncover more about our cosmic neighborhood, one truth becomes clear. The story of exploration is far from over. In fact, it is only just beginning. At Infinity Beyond, we believe that the next chapter of humanity's journey will be defined not by where we've been, but by where we dare to go next. For now, our robotic explorers are the vanguard. Spacecraft like Voyager, Pioneer, New Horizons, Perseverance, and James Webb Space Telescope have extended our senses into realms we may never reach in person. They have sent us images from alien skies, whispers from ancient rocks, and clues about the possibility of life beyond Earth. But the future promises something far more ambitious, a new age of interstellar exploration. One of the most exciting ideas on the horizon is Breakthrough Starshot, a bold initiative to send tiny, laser-powered probes to Alpha Centauri, our nearest stellar neighbor, located just over 4.3 light-years away. These probes, each no bigger than a smartphone, would ride on ultra-thin light sails, accelerated to 20% the speed of light by massive ground-based lasers. If successful, they could reach Alpha Centauri in just over 20 years. Though still in its early design phase, this concept represents a major leap forward, a shift from planetary exploration to interstellar reconnaissance. It's not just about visiting new worlds. It's about building the infrastructure and ambition needed to become a truly spacefaring civilization. Meanwhile, other ideas are being explored for long-range missions within our own solar system. Nuclear-powered propulsion systems, like nuclear thermal rockets or fusion drives, could cut travel time to Mars, Jupiter, and beyond. Concepts like space elevators, asteroid mining, and terraforming are moving from science fiction into early scientific planning. Perhaps the most audacious proposal is the creation of generation ships, enormous spacecraft designed to carry human populations on multi-century voyages to distant star systems. These would be self-contained ecosystems, with generations living and dying on board before their descendants arrive at a new world. While technologically daunting, such concepts force us to think long-term, beyond political cycles, lifespans, or immediate returns. But space is not just a destination. It is a test, a proving ground for our species. Colonizing Mars will test our resilience. Reaching Europa or Titan will test our ingenuity. Searching for life on distant exoplanets will test our humility. And exploring beyond the solar system will test our unity, because no one nation can cross the stars alone. International collaboration is already growing. NASA, ESA, Roscosmos, JAXA, and private companies like SpaceX and Blue Origin are working on crewed missions to the Moon, Mars, and deep space. The Artemis program, for example, will return humans to the Moon and eventually establish a permanent base. This lunar gateway could be a launchpad for Mars, or even a test site for life support systems designed for the outer solar system. Artificial intelligence, robotics, and biotechnology will also play critical roles. From self-repairing spacecraft to autonomous exploration bots and enhanced human physiology, we are approaching a point where the boundaries between biology and machine blur, unlocking new ways to adapt to space. At Infinity Beyond, we view the cosmos not just as a wilderness to explore, but as a mirror reflecting who we are, what we fear, and what we aspire to become. The future of space exploration will be shaped by science, but also by courage, imagination, and cooperation. Because when we finally step beyond the solar system, when our ships ride the light between stars, it won't just be a technological triumph. It will be the fulfillment of an ancient longing, written into the DNA of a curious species that has always looked up and asked, "What's out there?" From the scorched plains of Mercury to the icy edges of the Kuiper Belt, from Martian valleys carved by ancient rivers to alien moons hiding dark oceans beneath frozen crusts, from storms swirling on Jupiter to distant exoplanets circling foreign stars. This journey through our solar system has revealed not just a collection of celestial bodies, but a story of change, of chaos, of creation, and perhaps of life. At Infinity Beyond, we believe that space exploration is more than just a scientific mission. It is a human journey. Each world we visited, either by telescope, robot, or imagination, has told us something profound about who we are, where we came from, and what our future might hold. The solar system is no longer a set of dots in the sky. It is a living archive of cosmic history. Planets tell the story of planetary birth. Moons whisper of oceanic secrets. Rings echo the collisions of ancient worlds. And comets carry the icy signatures of formation itself. We've seen that Earth is not isolated or unique in structure. Venus and Mars once walked parallel paths, only to diverge. Europa and Enceladus may hold the keys to life's origins. Titan mimics our hydrological cycle with a chemistry all its own. Even tiny Pluto, cast aside as a dwarf planet, displays a world rich in geological complexity and beauty. And yet, with all we have discovered, the most humbling truth remains. We have only scratched the surface. There are thousands of moons left to study. Millions of asteroids waiting to be mapped. Billions of exoplanets beyond our reach. For now. The great questions remain. Are we alone? Are we the first? Or just one thread in a grand cosmic tapestry of life? The answers will not come easily. They may take generations, lifetimes, and centuries. But they will come. Because humanity is built to explore. It is our nature to sail across unknown seas, climb unreachable heights, and reach for stars beyond the darkness. The tools we now hold, telescopes that can see back in time, rovers that crawl across alien worlds, and spacecraft that whisper from interstellar space, are not the end of our progress. They are the beginning of our legacy. And that legacy is not reserved for scientists, astronauts, or billionaires. It belongs to all of us. Every child who looks up in wonder. Every person who dares to ask, "What's out there?" Every dreamer who sketches rockets in notebooks or watches the stars from their rooftop. To you, we say, keep wondering, keep asking, keep pushing. Because the future of exploration depends not on machines alone, but on hearts that burn with curiosity. As we end this journey through the enigmas of our solar system, remember, this is not the final chapter. It is the end of Volume 1 in a story that will span millennia. The stars are calling. The silence between them is not empty. It is waiting. And somewhere, far beyond the edge of what we know, the next great discovery is already out there, waiting for someone, maybe even you, to find it. We are infinity beyond, and this is only the beginning. Like Uranus, Neptune's atmosphere is rich in hydrogen, helium, and methane, but it radiates significantly more internal heat than Uranus does, despite being farther from the Sun. This internal energy likely fuels its extreme weather systems and turbulent cloud bands. Neptune also possesses a complex magnetic field, tilted and offset like Uranus's, further challenging our models of planetary magnetism. Neptune's largest moon, Triton, is another standout. Unlike most moons, Triton orbits Neptune in a retrograde direction, opposite the planet's rotation, suggesting it was captured rather than formed in place. Triton is one of the coldest objects in the solar system, yet it shows signs of geological activity. Geysers of nitrogen ice erupt from beneath its surface, hinting at internal warmth. Triton may also harbor a subsurface ocean, making it a candidate, albeit a distant one, in the search for habitability. Despite their size and significance, Uranus and Neptune remain largely unexplored. Only one spacecraft, Voyager 2, has ever flown past them. In the late 1980s, the flybys revealed tantalizing hints but left many questions unanswered. New missions are being proposed, including orbiters and atmospheric probes, to study these icy giants in depth. These missions could reveal more about exoplanets too, as many of the planets we've discovered around other stars are similar in size and composition to Uranus and Neptune. At Infinity Beyond, we see the ice giants as keys to understanding the broader architecture of planetary systems. They are mysterious, powerful, and beautiful. Reminders that even on the outer edges of sunlight, nature has crafted worlds of stunning complexity. Beyond the orbit of Neptune lies a realm of darkness and ice, a mysterious frontier where sunlight is dim and time seems to stretch. This is the Kuiper Belt, a vast ring of icy bodies and dwarf planets that extends billions of kilometers into space. At Infinity Beyond, we see this distant region not as the end of the solar system, but as a new beginning, one filled with ancient secrets and uncharted worlds. For decades, Pluto was considered the 9th planet of the solar system, its icy orbit dancing through the outermost reaches of the Sun's gravitational grasp. But in 2006, Pluto was reclassified as a dwarf planet by the International Astronomical Union. This decision sparked passionate debate, but it also opened the door to a broader understanding of the diverse and dynamic world Pluto truly is. In 2015, NASA's New Horizons spacecraft performed the first flyby of Pluto, transforming it from a blurry point of light into a stunning, complex world. What we saw was breathtaking. Vast plains of nitrogen ice, towering water ice mountains, a thin blue atmosphere, and a massive heart-shaped glacier named Tombaugh Regio. Even more astonishing, Pluto shows signs of ongoing geological activity, despite its small size and frigid location. Pluto's surface is young in many areas, with few craters and flowing nitrogen glaciers, suggesting that heat is still moving from the interior. Beneath the icy crust may lie a subsurface ocean of water, kept liquid by heat from radioactive decay. This hidden ocean raises fascinating questions. Could it support microbial life? Could Pluto, so distant and cold, be more than just a frozen relic? Orbiting Pluto is Charon, its largest moon, so large relative to Pluto that the two bodies actually orbit a common center of gravity outside Pluto itself. Charon's surface shows signs of ancient fractures and possible cryovolcanism, hinting that it, too, may have once been geologically active. The Pluto-Charon system behaves more like a binary planet than a typical planet-moon pair. But Pluto is not alone. The Kuiper Belt is home to thousands of other icy worlds. Among the most notable is Eris, a dwarf planet slightly smaller than Pluto, but more massive. Discovered in 2005, Eris played a major role in triggering Pluto's reclassification. Its highly elliptical orbit takes it far beyond Pluto, into regions where temperatures plunge below 240 degrees, to 400 degrees. There's also Makemake, Haumea, and countless unnamed objects that drift in silent orbits, worlds that may hold clues to the solar system's formation and evolution. These are remnants of the primordial disk from which the planets formed. Icy time capsules preserving the chemistry of the early solar system. Despite their distance and remoteness, missions to the Kuiper Belt are gaining momentum. New Horizons, after its Pluto encounter, went on to visit Arrokoth, a contact binary object shaped like a flattened snowman. This revealed insights into how planetary building blocks may have gently merged in the early solar system, rather than violently collided. Future missions are being proposed to orbit Pluto or explore multiple Kuiper Belt objects, KBOs. These missions would help answer fundamental questions. How did these icy worlds form? Do they possess oceans beneath their crusts? Could life, even primitive and microbial, exist in such extreme environments? At Infinity Beyond, we view the Kuiper Belt not as the edge of the known, but as a threshold. It marks the border between what we've explored and what still waits in the deep unknown. And in this distant expanse, these small frozen worlds may hold keys to understanding how planetary systems emerge, and how life might arise even in the coldest corners of the cosmos. Beyond the orbits of Pluto and the icy bodies of the Kuiper Belt lies a domain so vast, so distant, that light from the sun takes hours or even days to reach it. This is the true outer frontier of our solar system, a region not bound by planets, but by invisible forces and ancient clouds of icy debris. At Infinity Beyond, we consider this the boundary between home and the great interstellar ocean beyond. The first major landmark in this distant realm is the heliosphere, a vast, bubble-like region of space dominated by the solar wind. This stream of charged particles, ejected constantly from the sun, flows outward in all directions, creating a protective shield that deflects much of the dangerous cosmic radiation from deep space. The edge of this bubble, known as the heliopause, is where the solar wind slows down and yields to the interstellar medium, the thin soup of gas, dust, and particles that exists between the stars. The heliosphere defines the physical edge of our sun's influence. It stretches more than 120 astronomical units, AU, from the sun. That's over 18 billion kilometers, 11 billion miles. Crossing this invisible frontier marks the moment a spacecraft leaves the sun's neighborhood and enters true interstellar space. Only two human-made objects have ever reached this point: Voyager 1 and Voyager 2. Launched in 1977, these spacecraft were originally intended for planetary flybys. But thanks to precise engineering and a rare planetary alignment, they became ambassadors to the stars. Voyager 1 crossed the heliopause in 2012, and Voyager 2 followed in 2018. Though their instruments are aging and their power fading, they continue to send back data, messages from the edge of the solar system.
Orbiting Jupiter are four of the most extraordinary moons in the solar system. Io, Europa, Ganymede, and Callisto. These Galilean moons, discovered by Galileo Galilei in 1610, are not mere satellites. They are complex, dynamic worlds in their own right, each one unique in its geology, composition, and scientific potential. At Infinity Beyond, we often say that if you want to see the diversity of planetary environments, you don't need to leave Jupiter's neighborhood. Let's begin with Io, the innermost of the Galilean moons. Io is the most volcanically active body in the solar system. Its surface is a chaotic landscape of sulfur plains, lava lakes, and erupting volcanoes. These volcanic plumes can rise hundreds of kilometers into space. What drives this incredible activity is tidal heating. Gravitational forces from Jupiter and neighboring moons flex Io's interior, generating enormous friction and heat. Io has no known subsurface ocean, but its volcanic processes offer insights into the internal dynamics of rocky worlds. Next is Europa, perhaps the most tantalizing moon in the search for extraterrestrial life. Covered in a smooth shell of ice, Europa conceals a vast subsurface ocean, one that could be as much as 100 kilometers deep. This ocean is kept liquid not by sunlight, but by tidal heating. Europa's cracked and ridged surface suggests that the ice is dynamic, moving and flexing as the interior warms it from below. Observations from the Hubble Space Telescope and the Galileo spacecraft suggest that water plumes may be erupting through the ice, offering a direct path to sample the ocean without having to drill. If microbial life exists anywhere in the outer solar system, Europa is a prime candidate. Its ocean may be in contact with the moon's rocky mantle, potentially enabling hydrothermal vents similar to those found in Earth's deep oceans. Ecosystems that thrive without sunlight, using chemical energy instead. The upcoming Europa Clipper mission will investigate these possibilities in detail, scanning the ice, probing for signs of habitability, and seeking the building blocks of life. Then there's Ganymede, the largest moon in the solar system, even bigger than the planet Mercury. Ganymede is unique among moons because it has its own magnetic field, likely generated by a liquid iron or iron sulfide core. This field interacts with Jupiter's powerful magnetosphere, creating auroras that dance across its poles. Ganymede, too, is believed to harbor a subsurface ocean, possibly layered between sheets of ice. Its surface is a mix of dark, ancient terrain and lighter grooved regions, shaped by tectonic activity. Ganymede is a frozen world, but not a still one. Lastly, Callisto sits farthest from Jupiter and is the most heavily cratered object in the solar system. Its battered surface has remained largely unchanged for billions of years, preserving a record of the early solar system. Despite its apparent geologic inactivity, Callisto may also possess a subsurface ocean. Its distance from Jupiter shields it from intense radiation, making it a candidate for future human bases, should we ever venture that far. Together, these moons showcase a spectrum of planetary possibilities: volcanic fire, icy oceans, magnetic fields, and ancient records. They remind us that not all potentially habitable worlds are planets, and that in the shadows of giants, life might quietly stir. At Infinity Beyond, the Galilean moons are a solar system within a solar system, 4 worlds orbiting one, each pulling us deeper into questions of habitability, geology, and life. As we send more missions, capture more data, and one day perhaps even land on these distant shores, we edge closer to answering a question that has echoed across centuries. Are we alone? Beyond the orbit of Jupiter lies one of the most visually breathtaking worlds in the solar system, Saturn. With its iconic rings and otherworldly moons, Saturn captivates both scientists and stargazers alike. At Infinity Beyond, we regard Saturn not only as a giant of gas and gravity, but as a symbol of cosmic elegance, a planet that reveals how beauty and mystery often go hand in hand in the universe. Saturn is the second largest planet in our solar system, yet it's the least dense. so light, in fact, that it would float in water if there were a bathtub large enough to hold it. Composed mainly of hydrogen and helium, Saturn is similar in structure to Jupiter, though its atmospheric patterns are more subtle. Beneath its golden clouds, however, lies a planet of complex storms, including a massive, persistent, hexagonal jet stream at the North Pole, a geometric structure that has baffled scientists since its discovery. But Saturn's most famous feature, without question, is its rings. Unlike the faint ring systems of other gas giants, Saturn's rings are vast, bright, and intricate. Spanning over 280,000 kilometers, about 175,000 miles, but just tens of meters thick, they are composed mostly of ice particles, from tiny grains to massive chunks the size of houses. The origin of these rings is still debated. They may be remnants of a shattered moon, torn apart by Saturn's gravity, or they may have formed early in the planet's history from leftover material during its formation. Though visually stunning, Saturn's greatest scientific treasures may lie among its moons, and it has more than 150, including provisional ones. Two stand out as especially fascinating: Titan and Enceladus. Titan, the largest of Saturn's moons, is unique in the solar system. It's the only moon with a thick atmosphere, denser than Earth's, and it's composed primarily of nitrogen, with traces of methane and complex hydrocarbons. The surface of Titan is cold, averaging 179 degrees, 290 degrees, but it hosts lakes and rivers, not of water, but of liquid methane and ethane. Radar mapping has revealed mountain ranges, dune fields, and even rainstorms. It's an alien world with a familiar hydrological cycle driven not by water but by hydrocarbons. Beneath Titan's icy crust may lie a vast subsurface ocean of liquid water and ammonia. This makes Titan a potential candidate for life, not just in its ocean, but also in its complex chemistry. The upcoming Dragonfly mission, set to launch in the 2030s, will explore Titan's surface with a rotorcraft lander, studying its chemistry and searching for signs of prebiotic processes. Then there is Enceladus, a small moon with an outsized impact. Despite its modest diameter of just 500 kilometers, 310 miles, Enceladus has become a key target in the search for life. In 2005, NASA's Cassini spacecraft discovered massive geysers erupting from its south pole, jets of water vapor, ice, and organic molecules shooting into space. These plumes originate from a global subsurface ocean, kept warm by tidal forces from Saturn. Cassini flew through these plumes multiple times, sampling the spray directly. It detected salts, simple and complex organics, and evidence of hydrothermal activity on the seafloor, conditions that on Earth support entire ecosystems. If life exists in Enceladus's ocean, it could resemble microbial life found near Earth's deep-sea vents. At infinity beyond, Saturn is more than just rings and clouds. It is a system teeming with possibilities. From the methane seas of Titan to the icy fountains of Enceladus, Saturn challenges our assumptions about where life could exist and reminds us that the solar system is far more diverse and more alive than we once imagined. As we voyage beyond Saturn's magnificent rings, the outer reaches of our solar system begin to take on a strange and haunting beauty. Here lie the ice giants, Uranus and Neptune, two worlds that defy expectations and continue to perplex scientists. At infinity beyond, we regard these distant giants as cosmic enigmas, planets that hide powerful secrets beneath their icy exteriors and turbulent skies. Uranus, the seventh planet from the Sun, is often overlooked in favor of flashier worlds, yet it is one of the most bizarre planets in the solar system. Tilted at an angle of nearly 98 degrees, Uranus essentially rolls around the Sun on its side. This unusual axial tilt results in extreme seasonal changes that last over 20 years, with one hemisphere bathed in constant sunlight and the other plunged into prolonged darkness. Its pale blue-green hue comes from methane in its atmosphere, which absorbs red light and reflects blue. But beneath this calm exterior lies a surprisingly dynamic and mysterious world. Uranus is composed mostly of hydrogen, helium, and a dense mix of water, ammonia, and methane ices. It is surrounded by a faint set of rings and has at least 27 known moons, some of which may have been captured from the Kuiper belt. What's most puzzling about Uranus is its internal structure and magnetic field. Unlike Jupiter and Saturn, Uranus seems to lack the same intense internal heat. It emits very little energy. Its magnetic field is wildly tilted and offset from the planet's center, suggesting a strange internal dynamo. Scientists believe that beneath the upper atmosphere lies a superionic ocean, a bizarre phase of water that conducts electricity like metal. Then there's Neptune, the eighth and farthest known planet from the Sun. Slightly smaller than Uranus, but more massive, Neptune is a vivid blue world with some of the most violent weather in the solar system. Winds on Neptune can exceed 2,000 kilometers per hour, 1,200 miles per hour, making them the fastest recorded in the solar system. Its atmosphere hosts massive dark storms, analogous to Jupiter's Great Red Spot, that appear and vanish over time. For centuries, humans viewed the solar system as a perfect mechanism, planets orbiting the sun like gears in a finely tuned celestial clock. But discoveries made in recent decades, especially from missions like Messenger, have shattered that old illusion. What we now understand is far more chaotic. Mercury's eccentric orbit, chemical anomalies, and iron-rich core all point to a past shaped by violent disruptions and cosmic chance. The long-standing assumption was that the planets had always orbited the Sun in their current positions, with only minor fluctuations. But as scientists examined Mercury's composition, especially its unexpectedly high levels of volatile elements like potassium and sulfur, it became clear that the planet likely did not form so close to the Sun. These volatile elements should have been vaporized during Mercury's formation if it had originated in such an intensely heated region. Their presence hints at an origin further out in the solar system. This theory gains weight when combined with orbital mechanics and gravitational modeling. Researchers now believe that in the early solar system, planetary orbits were far more unstable than today. As the rocky planets were forming, they were surrounded by countless planetary embryos, moon-sized bodies formed from leftover debris. These bodies frequently collided, merged, or were ejected from the system altogether. Amid this chaos, Mercury's journey may have taken it from a stable, temperate zone, possibly even beyond Earth's current orbit, into the scorching inner solar system. And the force behind this dramatic relocation? Jupiter. Jupiter, the solar system's largest and oldest planet, exerts enormous gravitational influence. As it migrated slightly inward and then outward during the early years of the solar system, it likely disturbed the orbits of nearby forming planets. One of the victims of this gravitational disruption may have been the infant Mercury. Computer models simulate a scenario where Jupiter's shift alters the orbits of nearby planetary embryos, causing them to crash into one another or be flung toward the Sun. Mercury may have been one such casualty, thrown on an inward spiral where it ultimately collided with another young planet. The collision stripped away Mercury's outer layers, leaving behind a dense metallic core and an eccentric orbit forever marked by its traumatic past. This history not only explains Mercury's strange features, but also reinforces a deeper understanding of planetary migration, a concept once thought implausible. We now know that planetary systems are not fixed in time or space. Planets can move drastically during their youth, driven by gravitational interplay, collisions, and chaos. What we see today in our night sky is a snapshot of a long, tumultuous process of evolution and destruction. The implications are profound. If Mercury could form farther from the Sun and be hurled inward, then other planets, perhaps even Earth, may also have experienced significant migrations. This shifts how we think about habitability and planetary stability. It means that being in the Goldilocks zone may be a temporary condition, not a permanent feature. At Infinity Beyond, these ideas fuel an exciting narrative. The solar system is not a serene dance of planets, but a battlefield of gravity, heat, and chance. Every world bears scars of this ancient chaos, and Mercury wears them most vividly. It is a testament to the fact that even small worlds, seemingly static and insignificant, can have the most dramatic and violent backstories. As our exploration tools grow more advanced, we may yet discover more secrets locked in Mercury's strange orbit and metallic heart. For now, it stands as the solar system's ultimate survivor, bruised, battered, but still orbiting, whispering stories of a time when the heavens themselves were in flux. In the early days of planetary science, models of the solar system treated it like a perfectly balanced equation. One star, a set number of planets, each tracing a precise and eternal path around the sun. But as the field matured, this simplistic view gave way to something far more complex and dynamic. Thanks in large part to mathematical modeling and space exploration data, we now understand that the solar system behaves more like a chaotic system, one where tiny changes can create enormous and unpredictable outcomes over time. At the heart of this transformation in understanding lies a basic principle of physics, the n-body problem. In a simplified system with only one planet orbiting a star, it's relatively easy to predict the future path of that planet using Newton's laws of motion and gravitation. But once you introduce a second or third planet, the problem becomes exponentially more complicated. The gravitational interactions between multiple bodies, such as Mercury, the Sun, and Jupiter, produce outcomes that can no longer be predicted with absolute certainty. Instead, we enter the realm of chaos theory. This concept of orbital chaos is crucial to explaining the strange journey of Mercury. If it had remained in a stable, solitary orbit, its current position and composition would make no sense. But in a solar system filled with gravitational tugs and nudges from massive planets like Jupiter and Saturn, Mercury's path could easily have been altered, not once, but many times over millions of years. What Infinity Beyond highlights through data from missions like Messenger is that Mercury may have formed far from its current location. In the early solar system, it likely occupied a cooler, more temperate region, perhaps beyond Earth's orbit. In this more distant neighborhood, volatile elements like sulfur and potassium could have survived the formation process, becoming embedded in Mercury's crust. Then, through a series of gravitational perturbations, its orbit may have gradually, or even abruptly, shifted inward. Such movements are not just theoretical, they're supported by complex simulations of early solar system evolution. These models demonstrate how planets can be nudged by passing debris, minor interactions with other planets, or even large-scale migrations caused by the movement of gas giants like Jupiter. One particularly dramatic theory proposes that after being flung inward, Mercury collided with a planetary embryo of similar size. The resulting impact stripped Mercury of its lighter rocky layers, leaving behind the iron-heavy core we see today. This would also explain its highly elliptical orbit, far more stretched out than that of any other planet in the solar system. Today, Mercury's orbit is so eccentric that its distance from the Sun varies by tens of millions of kilometers during each revolution. This variation causes dramatic changes in surface temperature and affects the way the Sun appears in Mercury's sky, growing larger and smaller over the course of its orbit, sometimes even appearing to reverse direction. What's even more fascinating is that this unpredictability isn't just a relic of the past. Mercury's orbit continues to be influenced by the gravitational pull of other planets, making its long-term path difficult to predict with high precision. Over spans of millions or billions of years, these subtle forces could cause Mercury's orbit to shift again, potentially destabilizing nearby orbits or even creating conditions for future planetary collisions. From the perspective of Infinity Beyond, Mercury is not merely a battered relic from the dawn of the solar system. It is a vivid illustration of how chaos, rather than order, shaped our celestial neighborhood. Its current orbit, composition, and density all point to a dramatic past marked by migration, impact, and instability. In many ways, Mercury is the planetary equivalent of a survivor, having endured the worst the early solar system had to offer, and emerging as a testament to resilience amid cosmic upheaval.
Mercury, small, scorched, and long overshadowed by its planetary siblings, was for decades considered geologically simple and unremarkable. As the closest planet to the Sun, it was assumed to be a barren world, scorched by relentless solar radiation and stripped of anything interesting. But this perception changed drastically with the arrival of NASA's Mariner 10 mission in 1974. Although the spacecraft only imaged about 45% of Mercury's surface, what it revealed was startling. A heavily cratered, ancient world resembling the Moon, but with key differences that hinted at a much more complex history. Then came Messenger, a groundbreaking mission that orbited Mercury from 2011 to 2015. Thanks to its sophisticated imaging tools and spectrometers, scientists were able to map nearly the entire surface of Mercury, uncovering secrets hidden for billions of years. For the first time, the planet's terrain was seen in detail, exposing countless craters, mysterious smooth plains, and massive fault scarps, clues to a violent and dynamic past. Among Mercury's many features, one stands out for its sheer scale, the Caloris Basin. This immense impact crater measures over 1,500 kilometers across and was likely formed around 3.9 billion years ago during a period known as the Late Heavy Bombardment. The energy released in the collision that created Caloris was so powerful that it didn't just reshape the local surface, it rippled through the entire planet. On the opposite side of Mercury, in what scientists call the antipode of the Caloris Basin, lies a bizarre region known as the Weird Terrain. This jumbled and chaotic landscape is believed to have formed as a result of shock waves converging on the opposite side of the planet from the impact. But impact craters were only the beginning. Messenger revealed something no one had expected. Despite its proximity to the Sun, Mercury appears to have water ice in permanently shadowed craters near its poles. These regions never see direct sunlight due to Mercury's almost non-existent axial tilt. Combined with the lack of atmosphere, these deep polar pockets remain cold enough to preserve ice for potentially millions of years, just meters away from areas experiencing extreme solar heat. Even more surprising was the planet's composition. Conventional models predicted that Mercury, being so close to the Sun, would be depleted of volatile elements like potassium and sulfur. But Messenger detected these elements in unexpectedly high concentrations. In fact, potassium on Mercury exists at levels 10 times higher than on the Moon or Earth. This posed a major puzzle. These elements should have been vaporized in the early high-temperature environment near the Sun. Their presence suggested that Mercury either formed elsewhere in the solar system or that our understanding of planetary formation was incomplete. This led to a dramatic reconsideration of Mercury's origin. Rather than forming in its current location, some models now suggest that Mercury was born much farther from the Sun, perhaps even beyond the orbit of Venus or Earth. At that greater distance, it would have been easier for volatile elements to become incorporated into its formation. Later, due to gravitational interactions with other planets, especially the mighty Jupiter, Mercury may have been flung inward toward the Sun in a chaotic reshuffling of the early solar system. Such a journey would explain not only its current position, but also its high density. Mercury has the largest core relative to its size of any planet in the solar system. About 75% of its radius is molten metal. This core generates a magnetic field, something unexpected in such a small planet, and evidence that Mercury is still geologically active beneath its surface. At infinity beyond, this planetary enigma serves as a prime example of how initial assumptions can be shattered by data. From mysterious ice near the Sun to a massive iron core and a complex, volatile history, Mercury has gone from a planetary afterthought to one of the most compelling objects in the inner solar system. As scientists from infinity beyond and around the world continued to analyze the wealth of data returned by Messenger, Mercury's status as a planetary mystery only deepened. One of the most striking findings was just how dense the planet truly is. Mercury is the densest planet in the solar system, even denser than Earth when corrected for gravitational compression. This extreme density is due to its enormous metallic core, which occupies around 75% of the planet's entire radius and nearly half of its mass. This raised yet another intriguing question. Why does Mercury have such a disproportionately large core? The answer may lie in one of the most violent episodes in its history, a cataclysmic collision in the early solar system. According to a leading theory, young Mercury may have been involved in a massive planetary impact with another embryonic world. This impact was so extreme that much of Mercury's outer silicate crust and mantle were blasted into space, leaving behind a stripped-down, core-heavy world. Evidence supporting this theory comes from Mercury's heavily cratered and chemically distinct surface, as well as its lopsided magnetic field. Unlike Earth's magnetic field, which is fairly symmetrical, Mercury's magnetic field is offset significantly toward the north. This suggests unusual dynamics within the planet's interior and provides further clues to the planet's tumultuous past. The aftermath of that colossal impact might have also altered Mercury's orbital path. Today, Mercury follows the most eccentric orbit of any planet in the solar system. It swings dramatically between its closest and farthest points from the Sun, something that would be consistent with a world thrown off course by a massive gravitational event. This elliptical orbit contributes to Mercury's extreme temperature variations, with daytime highs soaring above 430 degrees and nighttime lows plummeting to 180 degrees. Even more puzzling was the fact that Mercury, despite its proximity to the Sun and apparent lack of geological activity on the surface, still maintains a magnetic field. This means the core is at least partially molten and capable of generating a dynamo effect, much like Earth's. The expectation for such a small planet was that it would have cooled and solidified billions of years ago, losing the internal heat necessary for such magnetic activity. But Messenger's data proved otherwise. Mercury's internal engine is still running. A new model for Mercury's internal structure began to take shape. Scientists propose that the planet consists of a solid silicate crust and mantle, beneath which lies a solid shell of iron sulfide. This layer surrounds a liquid outer core and potentially a solid inner core at the planet's center. Such complexity was wholly unexpected and challenged every existing model of planetary formation in the early solar system. The implications were profound. The idea that planets could form with such diversity, and that their destinies could be so drastically shaped by early impacts and migrations, revolutionized our understanding of planetary evolution. Mercury's story suggested that even small, seemingly barren planets could have rich, dynamic histories. Beyond the planet itself, the story of Mercury tells us something larger about the nature of the solar system. It is not the stable, clockwork-like system we once believed. Instead, it is a chaotic environment where gravitational interactions between planets can shift entire orbits, cause collisions, and alter planetary destinies. Mercury, flung inwards and stripped of its outer layers, stands as the starkest example of this cosmic turbulence. Today, thanks to missions like Messenger and the interpretations made possible by teams like those at Infinity Beyond, Mercury is no longer dismissed as a lifeless rock too close to the Sun to matter. It has emerged as one of the most compelling windows into the violent, unpredictable, and awe-inspiring history of our solar system's formative years.
As our robotic explorers continue to peel back the secrets of Mars, the next frontier looms large, sending humans to the Red Planet. At Infinity Beyond, we see this not just as an engineering challenge, but as one of the most ambitious dreams humanity has ever dared to pursue, a step toward becoming a truly multiplanetary species. The concept of a manned mission to Mars has existed for decades, living in the pages of science fiction novels and echoing in the ambitions of space visionaries like Wernher von Braun and Carl Sagan. But now, with rapid advances in technology, international collaboration, and private spaceflight, that vision is beginning to take shape in the real world. NASA's Artemis program aims to return humans to the moon as a stepping stone for deeper space missions. The experience gained in operating on the lunar surface, especially establishing sustainable life support systems, in situ resource utilization, and long-term human health monitoring, will provide critical knowledge for an eventual trip to Mars. Meanwhile, agencies like SpaceX are pushing the boundaries even further. Elon Musk's vision of using the Starship launch system to carry humans to Mars has ignited a renewed sense of urgency and possibility. Though the timeline is still uncertain, the groundwork is being laid. Launch systems are being tested, closed-loop habitats are being designed. Simulated Mars bases have already been constructed on Earth, from deserts in Utah to volcanic slopes in Hawaii. But Mars will not welcome us easily. The journey alone takes 6 to 9 months, depending on planetary alignment. Once there, astronauts will face challenges never encountered before. Unbreathable air, bone-chilling cold, and gravity that is only 38% of Earth's. Radiation from the sun and cosmic rays pose significant risks in the absence of a strong magnetic field or thick atmosphere. Surface storms, though not violent, can last for weeks and plunge entire regions into darkness, complicating solar energy production and navigation. Life support must be airtight and resilient. Food, water, and oxygen cannot be entirely shipped from Earth. Instead, future Martian pioneers will need to generate resources on-site, extracting water from ice or regolith growing food in greenhouses and producing oxygen and fuel from the planet's carbon dioxide-rich atmosphere. These technologies are still in development, but are advancing steadily, tested through experiments on the International Space Station and Earth analogues. Yet, despite these hardships, the allure of Mars remains irresistible. Why? At Infinity Beyond, we believe it's because Mars offers something unique, a blank page in the story of humanity. To stand on another world and look up at a pale blue dot in the sky, to know that your home is one of countless stars away, is a profound shift in perspective. Mars represents more than exploration. It is a mirror in which we examine our ingenuity, our resilience, and our desire to reach beyond what we were told was possible. The psychological and philosophical implications of humans on Mars are as significant as the scientific ones. What kind of societies will we build on another world? How will we preserve our humanity in a place so alien? And what will it mean to be an Earthling living on Mars? These are the questions that fuel every simulation, every rover mission, and every launch. Mars is not just a destination. It is a proving ground for science, for survival, and for the spirit of exploration itself. At Infinity Beyond, we are watching this future unfold with wonder and anticipation. The first human footprint on Mars may be years or decades away, but the journey has already begun, and one day soon, that red dust will hold the marks of our ambition, our curiosity, and our courage. To understand what Mars can truly reveal to us, we must look beyond the present-day challenges and instead rewind the clock, back to a time when Mars was a young, warm, and potentially wet world. At Infinity Beyond, we believe the ancient past of the Red Planet holds the deepest answers to one of humanity's oldest questions. Are we alone? Roughly 3.5 to 4 billion years ago, Mars likely had a thicker atmosphere, warmer surface conditions, and abundant liquid water. In fact, the Noachian period, named after the biblical figure Noah due to its association with water, was marked by heavy bombardment, volcanic activity, and active hydrological systems. Valley networks, delta fans, and sediment layers all point to a planet that once experienced rainfall, flowing rivers, and perhaps even global oceans. These aren't just geologic curiosities, they're potential habitats. On Earth, wherever there is liquid water, there is life. From the scalding vents of the deep ocean to the frigid lakes beneath Antarctica's ice, microbial life finds a way to adapt and endure. If Mars had similar environments, stable lakes, volcanic warmth, and a chemically active atmosphere, then the basic conditions for life as we know it may have existed. The question is, did it? That's why Mars missions have focused on ancient lake beds and sedimentary regions, places like Gale Crater, where Curiosity discovered clay minerals that form only in neutral pH water, and Jezero Crater, where Perseverance is now investigating a once lush river delta. These sites are not chosen at random. They represent the best chances of preserving biosignatures, chemical or morphological traces of past life, locked in rock for billions of years. In many ways, Mars is more ideal for this search than Earth. On our planet, tectonic activity, erosion, and biological processes recycle or destroy much of the rock record. Mars, by contrast, is geologically quiet. Its ancient surfaces have remained largely undisturbed, preserving a planetary time capsule from the earliest epochs of the solar system. Imagine finding a microfossil in Martian rock, a clear imprint of life that arose independently of Earth. Such a discovery would fundamentally reshape our understanding of biology, evolution, and the prevalence of life in the universe. It would mean that life is not a miracle, but a natural outcome when the right ingredients come together. Even if life never existed on Mars, studying why it didn't emerge or why it failed to survive offers invaluable insight. It allows us to test the boundaries of habitability and refine our criteria for searching on other worlds. What if life nearly took hold, but Mars lost its magnetic field too soon, or dried out too quickly? These scenarios would help explain not just the silence of Mars, but perhaps the silence of the stars as well. Subsurface exploration may hold the key. As the surface grew more hostile over time, any microbial life may have migrated underground, where geothermal heat, subsurface ice, and protected niches could have extended habitability by millions or even billions of years. Future missions equipped with drilling systems and biosensors may one day reach these hidden reservoirs. At Infinity Beyond, we view the ancient Martian world as a mirror of early Earth, a stage that was set, a story that may have begun and then stopped. Whether it ended before life began or after it had already taken root remains one of the greatest enigmas in planetary science. But we will keep searching. In every rock sample, every spectral scan, every rover's dusty tread, we are chasing the echoes of ancient life. Because if Mars ever lived, then the universe is no longer silent. It has spoken once and may do so again. While ancient Mars may have once been a water-rich planet with flowing rivers and shallow seas, today's Martian landscape appears dry, desolate, and frozen. But looks can be deceiving. At Infinity Beyond, we believe the surface of Mars may not tell the full story. What lies beneath may yet surprise us, and perhaps even revolutionize our understanding of life beyond Earth. In recent decades, a growing body of evidence has hinted that liquid water might still exist on Mars, not on the surface, but deep underground. One of the most provocative discoveries came in 2018, when data from the European Space Agency's Mars Express radar instrument revealed something extraordinary beneath the southern ice cap, a region of high radar reflectivity, consistent with a subsurface lake of salty liquid water. This body, stretching around 20 kilometers wide, lies about 1.5 kilometers below the surface, kept liquid by pressure and salt content even in frigid temperatures. While this finding remains controversial and subject to further investigation, additional radar data collected in subsequent years has supported the idea of multiple briny water pockets beneath the polar cap. If confirmed, these underground reservoirs would be the most stable potential habitats for microbial life on modern Mars. Why underground? Because the Martian surface is incredibly hostile. The planet lacks a global magnetic field, allowing solar and cosmic radiation to bombard its surface continuously. Any surface-dwelling organism would need extraordinary protection to survive. Below the surface, however, conditions are far more favorable. Protection from radiation, potential heat from geothermal activity, and access to frozen or liquid water. Earth offers compelling analogues. Deep beneath the Earth's crust, bacteria have been found surviving in dark, pressurized environments, feeding on chemical energy derived from rocks, without sunlight or oxygen. These extremophiles prove that life can exist in conditions once thought impossible. If it can happen here, why not on Mars? As we leave the scorched landscapes of Venus and the delicate, life-sustaining balance of Earth, our attention turns to a world that seems both familiar and alien, Mars. Known for its rust-red hue and its prominent role in both science and science fiction, Mars is the fourth planet from the Sun and the most Earth-like of all other worlds in our solar system. At infinity beyond, we see Mars not merely as a dusty desert, but as a time capsule, a planet that once may have looked remarkably like our own. Despite its current barren appearance, Mars offers countless clues that it was once a very different place. Satellite images and rover missions have revealed the unmistakable signs of ancient riverbeds, dried lake basins, and even delta formations. These features are not speculation. They are geological evidence of water's enduring presence on the surface of Mars billions of years ago. One of the first breakthroughs came from NASA's Viking orbiters in the late 1970s. They revealed vast channels that could only have been carved by flowing liquid. Later missions, particularly Mars Global Surveyor and Mars Reconnaissance Orbiter, added layers of high-resolution imagery, exposing complex networks of valleys and mineral compositions that form only in the presence of water. Then came the rovers. Spirit and Opportunity, twin explorers sent by NASA in 2004, drastically changed our understanding of Martian history. They found clear signs of past hydrothermal activity, water-altered rocks, and minerals like hematite and gypsum that could only form in wet conditions. Later, the Curiosity rover, still operating today, discovered evidence that Gale Crater once held a long-lasting freshwater lake. Organic molecules, the building blocks of life, were detected in the sediments. All of this data points to one astonishing conclusion. Mars was once warm and wet, with a climate potentially suitable for life. Around 3.5 to 4 billion years ago, the red planet may have had a thicker atmosphere, a stable water cycle, and even a magnetic field to shield it from solar radiation, conditions remarkably similar to early Earth. So, what happened? At Infinity Beyond, we explore the prevailing theory that Mars lost its magnetic field early in its history. Without this protection, the solar wind, a stream of charged particles from the Sun, began stripping away the planet's atmosphere. Over millions of years, the once thick air thinned to a whisper, and with it, the ability to retain heat and water vanished. Mars transitioned from a potentially habitable world to a frozen desert. Today, Mars's atmosphere is less than 1% the density of Earth's. Temperatures fluctuate wildly, from a high of 20 degrees C, 68 degrees during the day, to lows of 100 degrees sun, 148 degrees at night. The water that remains is mostly locked in polar ice caps or exists as traces of vapor and salty brine in the soil. The planet is dry, cold, and hostile, but not lifeless in its past. The importance of Mars lies not just in its potential for ancient life, but in its accessibility. Unlike Venus, Mars has a surface we can explore with rovers, landers, and eventually humans. It has seasons, weather patterns, and polar ice. For all its challenges, it remains our best chance at exploring what a second genesis of life might look like, or what happens when planetary protection fails. As we study Mars with increasing precision, from orbit and on the ground, we are slowly unraveling the mystery of a world that may once have teemed with life. And at Infinity Beyond, we believe Mars holds the keys not only to understanding the past, but also to shaping the future of human exploration. While the surface of Mars appears cold, dry, and lifeless today, recent discoveries suggest that the red planet may still possess the ingredients necessary to support microbial life beneath its surface. At Infinity Beyond, this possibility sparks one of the most exciting scientific quests of our time, to determine whether life ever existed on Mars and whether it might still survive, hidden in the shadows of the Martian underground. One of the most compelling reasons to believe in this possibility lies in the evidence of subsurface water. In 2018, radar data from the European Space Agency's Mars Express orbiter revealed something remarkable beneath the southern polar ice cap, a 20-kilometer wide lake of liquid water buried under 1.5 kilometers of ice. This discovery, while still debated, opens the door to the existence of underground aquifers, environments shielded from the harsh surface where microbial life could potentially endure. Similar analogues exist here on Earth. Deep beneath Antarctica, in subglacial lakes such as Lake Vostok, microbes have been found thriving in complete darkness, under immense pressure, isolated from the surface for millions of years. If such extreme life forms can exist on Earth, why not on Mars? In addition to water, Mars presents seasonal plumes of methane, recorded by both orbiters and the Curiosity rover. Methane is unstable in the Martian atmosphere, breaking down rapidly under solar radiation. This means any methane observed must have been released recently. On Earth, over 90% of methane comes from biological processes. Could similar processes be occurring below the Martian crust? While methane can also be produced geologically, the cyclic and localized nature of its presence on Mars raises tantalizing questions. NASA's Perseverance rover, which landed in Jezero crater in 2021, was specifically designed to answer some of these questions. Jezero is an ancient river delta where water once flowed into a large lake. The delta's layered sedimentary deposits are ideal for preserving biosignatures, chemical or structural clues left behind by life. Equipped with instruments capable of detecting organic molecules, scanning rock cores, and caching samples for a future return to Earth, Perseverance represents our best chance yet to solve the Martian mystery. At Infinity Beyond, we follow every sample drilled, every spectrum analyzed, every grain of Martian soil examined. Because this mission is more than a robotic expedition, it is a direct search for ancient life on another world. And what's more thrilling is that we are planning to bring pieces of that world back home. The Mars Sample Return mission, currently in development through a collaboration between NASA and the European Space Agency, will attempt to retrieve the samples collected by Perseverance and return them to Earth by the early 2030s. Analyzing Martian soil and rock in Earth-based laboratories will provide levels of precision impossible to achieve remotely. If signs of microbial life, fossilized or preserved, are discovered, it would mark one of the most profound scientific achievements in human history. And even if no signs of life are found, the mission will still dramatically enhance our understanding of planetary formation, climate evolution, and the chemical pathways that lead to habitability. It will inform future crewed missions to Mars, providing crucial insights into soil chemistry, radiation exposure, and environmental hazards. The implications stretch far beyond Mars itself. If life once arose independently on the red planet, it suggests that life may be a common phenomenon in the universe, not a singular fluke confined to Earth. It would mean that given the right ingredients and time, the universe is likely teeming with biology, waiting to be discovered. At Infinity Beyond, we believe that in the dusty plains and ancient deltas of Mars, the past is whispering to us. We're listening, carefully, patiently, and with unshakable curiosity. As our robotic explorers continue to peel back the secrets of Mars, the next frontier looms large, sending humans to the red planet. At Infinity Beyond, we see this not just as an engineering challenge, but as one of the most ambitious dreams humanity has ever dared to pursue, a step toward becoming a truly multi-planetary species. The concept of a manned mission to Mars has existed for decades, living in the pages of science fiction novels and echoing in the ambitions of space visionaries like Wernher von Braun and Carl Sagan. But now, with rapid advances in technology, international collaboration, and private spaceflight, that vision is beginning to take shape in the real world. NASA's Artemis program aims to return humans to the moon as a stepping stone for deeper space missions. The experience gained in operating on the lunar surface, especially establishing sustainable life support systems, in situ resource utilization, and long-term human health monitoring, will provide critical knowledge for an eventual trip to Mars. Meanwhile, agencies like SpaceX are pushing the boundaries even further. Elon Musk's vision of using the Starship launch system to carry humans to Mars has ignited a renewed sense of urgency and possibility. Though the timeline is still uncertain, the groundwork is being laid. Launch systems are being tested, closed-loop habitats are being designed, simulated Mars bases have already been constructed on Earth, from deserts in Utah to volcanic slopes in Hawaii. Throughout this odyssey, we've marveled at the birth of stars, the scale of galaxies, the mystery of black holes, and the delicate dance of celestial bodies. We've explored theories about alien life, the nature of space-time, and the ultimate fate of the universe. And yet, for all we've uncovered, we are reminded of a humbling truth. We've only just begun. Our instruments grow sharper, our understanding deepens, but the cosmos still stretches beyond imagination, a tapestry so intricate that each discovery leads to new questions. What lies beyond the observable universe? Is there a multiverse? What caused the Big Bang? What happens after the last star dies? The pursuit of these answers is what makes us human. The universe isn't simply a place we live. It's a mystery we're meant to engage with, piece by piece, generation after generation. And make no mistake, this story is still unfolding. The tools of tomorrow, AI-driven telescopes, gravitational wave observatories, interstellar probes, will open doors we've only dared to knock on. The scientists and explorers of the next century may well find proof of life elsewhere, map other galaxies in full detail, or even unlock the secrets of time itself. But the most powerful part of this story is that you are part of it. Each time you look at the night sky and wonder, each time you read, question, imagine, that's the universe within you awakening. You are a witness to a grand cosmic evolution, a rare moment in time when life not only exists but begins to understand itself. The stars above you are not just distant points of light, they are echoes of creation, calling us forward. So, whether you are a scientist, a student, a dreamer, or simply someone captivated by the unknown, you are helping write this great story. With every question you ask, you turn the page, and maybe, someday, one of us will find the answer that changes everything.
Our universe, once nothing more than an infinitesimal speck, smaller than an atom, has now grown into a vast, mind-bending expanse stretching billions upon billions of light-years across. From that singularity came everything: time, space, matter. And in this unimaginable scale of cosmic wonder lies something rare, something extraordinary: planet Earth. Earth, the blue marble drifting in the black void, is the only place in the cosmos known to host life. It's our origin, the cradle of humanity, and the launchpad for our journey through the stars. But within the deep reaches of this universe dwell enigmas we have yet to comprehend. Hidden secrets that, if revealed, could forever transform our understanding of space, time, and existence itself. Thanks to rapid advancements in observational technology, modern astronomers are capturing images of stars, galaxies, cosmic collisions, and glowing nebulae, offering glimpses into distant epochs and faraway worlds. These are not just beautiful visuals, they are clues, fragments of a cosmic puzzle we are slowly piecing together. The Hubble Space Telescope, with over 1 million images captured, has become a symbol of our quest to reach beyond Earth. Meanwhile, the Kepler Space Observatory has identified over 4,000 exoplanets, some of which may closely resemble Earth and even support life. These revolutionary discoveries have ignited a shared sense of awe. The universe, it seems, is not just vast, it's majestic, filled with exotic energies and phenomena we barely grasp. From gamma-ray bursts that unleash the power of 1 billion suns to the infinitely dense mystery of black holes, the cosmos overwhelms us with its elegance and complexity. Yet, despite the breakthroughs and excitement, the truth remains. We are only at the beginning. The origin of life, the birth of the universe, and its ultimate fate. These remain veiled in mystery. Our knowledge of our own solar system is still incomplete, and our grasp of the greater universe? Even more limited. But that hasn't stopped us from venturing forward, asking questions, pushing boundaries, and daring to imagine what lies beyond. Despite our ability to detect exoplanets hundreds or even thousands of light-years away, there remains a puzzling absence of evidence for a massive celestial body believed to be hiding right within our solar system. This object is known as Planet 9, a theoretical planet lurking in the dark beyond Neptune. According to certain scientists, Planet 9 may possess a mass 5 to 10 times greater than that of Earth. Its orbit, if it exists, would be incredibly elongated, reaching as far as 20 times the distance between Neptune and the Sun. That's so distant that it would take this object between 10,000 to 20,000 years to complete a single orbit. Why do astronomers even suspect such a planet exists? The idea arose from strange observations, specifically the odd clustering and movement of trans-Neptunian objects in the Kuiper Belt. These small, icy bodies follow paths that don't make sense when considering the gravitational influence of the known planets alone. To explain these anomalies, scientists hypothesized that a hidden, massive planet might be exerting its gravity from the shadows, slowly warping the orbits of distant objects. But locating Planet 9 is no easy task. At such a distance, it would be unimaginably faint, up to 6.25 million times dimmer than Uranus, as seen from Earth. While similar dim asteroids can be spotted due to their quick motion across the sky, Planet 9 would move so slowly that it could easily be mistaken for a static background star. One might think we could use telescopes like Kepler to detect it, but those tools are optimized for a very specific purpose: detecting exoplanets by monitoring the dimming of light as a planet crosses in front of its host star. Planet 9, being part of our solar system and lacking a nearby star to eclipse, wouldn't trigger such a signal. To find it, scientists must rely on detecting the tiny amount of sunlight the planet reflects, a task akin to finding a cosmic needle in an endless, spinning haystack. Still, the mystery remains compelling. If Planet 9 does exist, it could explain much of the chaos at the edge of the solar system. If it doesn't, then something else entirely must be responsible, perhaps something even stranger. Some theories have proposed that Planet 9 could in fact be a primordial black hole, a tiny, ancient remnant from the birth of the universe. Such a black hole might have the same gravitational influence, but be as small as a grapefruit, completely invisible to telescopes. Others have floated the idea that Planet 9 could be a brown dwarf, a type of failed star that never ignited. These too would be difficult to detect with standard equipment due to their low light emission. Despite the uncertainty, hope lies ahead. The upcoming Vera C. Rubin Observatory, under the Legacy Survey of Space and Time, LSST, is expected to begin scanning the sky with an 8.4-meter mirror and a 3,200 megapixel camera. It will capture more of the cosmos in 1 year than all previous telescopes combined, and might finally reveal Planet 9, or something even more mysterious. with all efforts to spot Planet 9 using infrared and optical telescopes yielding no success. Scientists began asking an audacious question. What if Planet 9 isn't a planet at all? One compelling hypothesis is that Planet 9 could be a primordial black hole, a remnant from the earliest moments after the Big Bang. Unlike the stellar mass black holes formed by collapsing stars, primordial black holes would have originated during the universe's infancy, when everything was denser and hotter. If such a black hole had formed at the right moment, within just a tiny fraction of a second, it could possess a mass of 5 to 10 Earths, yet be no larger than a grapefruit. Think about that. An object with the gravitational pull of a planet, squeezed into something smaller than your fist. This minuscule size means that detecting it with telescopes is virtually impossible. It wouldn't reflect light like a planet, nor emit detectable heat. It would simply sit silently in the dark, bending space and subtly influencing the orbits of anything that ventured too close. What first drew astronomers to this possibility wasn't just the invisibility of Planet 9, but also some unusual star observations. In some instances, stars briefly appeared brighter, as if something had passed in front of them and focused their light, much like a lens. This effect is called gravitational lensing, and it can occur when a massive object, like a black hole, warps the light from a more distant star. Not only did the stars momentarily brighten, but their images also appeared to curve slightly, suggesting that a dense, transparent, and incredibly compact object had passed between us and the star. This triggered simulations involving primordial black holes, and the results were eerily consistent with the gravitational patterns seen in the Kuiper Belt. Moreover, a primordial black hole would not emit infrared radiation, explaining why traditional telescope scans have come up empty. If such an object were orbiting the Sun at an extreme distance, it might even mimic the exact influence attributed to the hypothetical Planet 9. Other scientists have speculated that the unseen object could be a brown dwarf, a celestial body that lies between a planet and a star in mass, but fails to undergo nuclear fusion. Like primordial black holes, brown dwarfs are notoriously difficult to detect, as they emit very little visible light. While each theory has its flaws, they all highlight a central truth. Something is out there. Whether it's a massive planet, a black hole, or a failed star, its presence is being felt, not through vision, but through the ripple effects in space. This cosmic detective story is far from over. Scientists are preparing new tools to deepen the search. The Vera C. Rubin Observatory, once fully operational, will scan the sky at unprecedented resolution. And even the James Webb Space Telescope, with its deep infrared capabilities, may help narrow the possibilities.
By the 1920s, as ground-based technology advanced, humanity began replacing imaginative speculations with actual data regarding Venus. Earlier, artists and scientists had imagined a world teeming with tropical forests or cloaked in mysterious gases, but spectroscopic analyses began to reveal otherwise. These analyses indicated that Venus's clouds were not filled with water or oxygen. Some scientists speculated that formaldehyde permeated its atmosphere, leading to the grim interpretation that Venus was not just dead, but essentially a pickled planet. However, everything began to shift during the 1950s. More accurate Earth-based observations showed that Venus's atmosphere was overwhelmed by an entirely different substance, carbon dioxide. This revelation rewrote our expectations. Venus was not shrouded in clouds of water or formaldehyde, but smothered in a thick, heat-trapping blanket of CO2. As was known from Earth's own experience with greenhouse gases, this could only mean one thing. Whatever existed beneath Venus's cloud cover must be unimaginably hot, likely too hot for any form of Earth-like life. With the arrival of space exploration, the challenge of reaching Venus became a daunting reality. The Soviet Union, leading the charge during the early space age, initiated a series of missions, in the 1960s under the Venera program. The goal was to penetrate the thick atmosphere and make direct contact with the surface. Initial efforts were riddled with failure. The early probes didn't even escape Earth orbit, but perseverance led to success. Venera 1, launched in February 1961, became the first spacecraft aimed at flying by Venus. Despite a successful launch, it experienced a complete telemetry failure. No data ever returned. As far as we know, Venera 1 still orbits the Sun silently today. Then came Venera 3, a more daring attempt. This mission was designed not just to fly by, but to enter Venus's atmosphere and attempt direct data collection. Unfortunately, after crossing into the atmosphere, all contact was lost. It crashed into the planet, becoming the first human-made object to make contact with the surface of another planet, even if it did so in silence. Swedish Nobel laureate Svante Arrhenius was among the early visionaries who speculated about Venus's potential for life. He believed its cloud cover consisted of water vapor and envisioned swamps and rainforests similar to Earth's Carboniferous period. In his book, The Destinies of the Stars, he described Venus as a stable, swampy world that hadn't undergone the same kind of evolutionary pressure that shaped life on Earth. These lush descriptions inspired generations of science fiction writers to imagine a world filled with ancient creatures and shadowy, vine-draped jungles hidden behind the clouds. Yet, ironically, Arrhenius is now better remembered for his work on Earth's climate, rather than his musings on extraterrestrial swamps. In 1896, he was the first scientist to demonstrate how gases like carbon dioxide can trap heat in a planet's atmosphere, a process now known as the greenhouse effect. This concept, vital to understanding climate change on Earth, would also become central to unlocking the true nature of Venus. As NASA and other space agencies like Infinity Beyond would later show, this greenhouse effect had a profound and catastrophic impact on Venus's climate. It explained how the planet had become the scorching inferno we now know today. As the space age gained momentum, the mysteries of Venus began to unravel further. While the early Venera missions struggled with partial or total failure, they represented a bold step toward demystifying our so-called sister planet. The Soviet program, though plagued with setbacks, pressed forward with determination. In doing so, it gradually overcame the technical challenges of sending probes into one of the most hostile environments in the solar system. The turning point came as probes began to detect overwhelmingly high levels of atmospheric carbon dioxide, along with crushing pressures and extreme temperatures. By the late 1960s, humanity was forced to abandon all romanticized notions of Venus being Earth-like. In fact, what emerged was a terrifying reality. Venus was an inferno, where surface temperatures soared above 860 degrees, and atmospheric pressure was over 90 times that of Earth. That's the equivalent of being 900 meters underwater. These revelations shattered old assumptions. Venus was not only unwelcoming, but deadly, an environment far removed from the life-bearing potential once imagined. Probes continued to fail under the intense conditions, often melting or being crushed before reaching the surface. Yet even in their failures, they provided invaluable data. Each mission taught scientists more about how to design resilient spacecraft capable of withstanding brutal planetary environments. By the 1970s, a clearer picture began to emerge. Infinity Beyond and other research centers utilized the gathered data to model the planet's climate, structure, and atmosphere. Radar imaging showed that Venus was a rocky wasteland, pockmarked with volcanic formations and dominated by plains formed from ancient lava flows. No water, no vegetation, no breathable air, just a hostile furnace under a choking CO2-rich atmosphere. One of the most dramatic contrasts between Venus and Earth lies in their evolutionary trajectories. Both planets are similar in size, mass, and overall composition. Yet they developed along radically different paths. Earth stabilized into a haven for life, while Venus became an example of planetary transformation gone awry. Much of this divergence is now understood through the lens of atmospheric science. The greenhouse effect on Venus ran out of control. Early in its history, Venus may have had shallow oceans or liquid water on its surface, but as solar energy increased over time, more water evaporated into the atmosphere. Water vapor itself is a greenhouse gas, so this created a feedback loop. More heat led to more evaporation, which led to even more heat. Eventually, the oceans boiled away completely, and the water molecules were broken down by solar radiation, hydrogen escaping into space, and oxygen reacting with surface minerals or being lost. Without water to remove carbon dioxide through weathering and sedimentation, CO2 built up unchecked in the atmosphere, trapping even more heat. What had once been a potentially habitable planet was transformed into a hellish pressure cooker. It is a cautionary tale, one that scientists at Infinity Beyond used as a case study to better understand the future trajectory of Earth's climate as well. Meanwhile, as the veil of Venus lifted, attention began to shift to other celestial bodies. Missions were being planned not just to fly by planets, but to orbit and map them in detail. This opened the door to another enigmatic world. Mercury, the closest planet to the Sun, and long thought to be little more than a scorched rock. But as we would soon discover, Mercury had its own story to tell, one full of violence, mystery, and unexpected surprises. And so the focus of exploration began to widen, with Mercury ready to step out of the shadows and into the spotlight of planetary science.
Beyond the heliopause lies the Oort cloud, a hypothetical sphere of icy bodies that surrounds the entire solar system like a cosmic shell. It is believed to stretch from about 2,000 AU to possibly 100,000 AU, more than a light year from the Sun. Though no spacecraft has ever reached it, the Oort cloud is thought to be the origin of long-period comets, those icy visitors with orbits lasting thousands of years. The objects in the Oort cloud are the ancient remnants of the early solar system, small frozen bodies that were flung outward by the gravitational chaos of the giant planets. Here, gravity is so weak that these objects are only loosely bound to the Sun and can be perturbed by passing stars or galactic tides. Studying the Oort cloud directly remains a future ambition. No current mission is capable of reaching it, but its existence helps scientists understand the architecture and evolution of our solar system and the mechanisms by which comets are delivered to the inner solar system. This far from the Sun, our solar system blends seamlessly into interstellar space, a realm filled with unknowns. It is in this deep cold where the journey to other stars begins. The nearest star system, Alpha Centauri, lies over 4.3 light-years away. Even the fastest spacecraft built by humanity would take tens of thousands of years to reach it. But the dream of crossing that immense gulf remains alive. Projects like Breakthrough Starshot aim to one day send ultra-fast probes to neighboring stars, using powerful laser sails to accelerate them to a significant fraction of the speed of light. These missions are still conceptual, but they represent a new kind of thinking, not just exploring our solar system, but stepping beyond it. At Infinity Beyond, the outer solar system is not an ending, but a threshold. It is the last whisper of home before the cosmic silence of interstellar space. And as we send our machines, our messages, and someday even ourselves across this great divide, we become something new. Interstellar travelers, reaching for the stars. As we pass beyond the heliosphere and drift through interstellar space, our attention turns outward, toward the stars themselves and the hidden worlds that orbit them. For centuries, humans looked to the night sky and wondered, are there other planets like Earth? Are we alone? At Infinity Beyond, these questions are not just philosophical, they are scientific pursuits. And in recent decades, the answers have begun to emerge. The term exoplanet refers to any planet outside our solar system, orbiting a star other than the Sun. For most of human history, these planets remained invisible, their existence purely speculative. But everything changed in 1992, when the first exoplanets were confirmed, strange, massive worlds orbiting a pulsar. Then in 1993, the first exoplanet around a Sun-like star, 51 Pegasi b, was discovered. It was a gas giant in a tight, scorching orbit, unlike anything in our solar system. Since then, our catalog has exploded. Thanks to missions like Kepler, TESS, Transiting Exoplanet Survey Satellite, and powerful ground-based telescopes, we have now identified over 5,500 confirmed exoplanets, with thousands more candidates waiting to be verified. They range from hot Jupiters that skim the surfaces of their stars to super-Earths, rocky planets larger than Earth but smaller than Neptune. We found mini-Neptunes, lava worlds, and even rogue planets wandering between stars without any sun to orbit. But the most exciting targets are the planets located in their star's habitable zone, the region where temperatures might allow for liquid water to exist on the surface. These so-called Goldilocks worlds aren't too hot or too cold, but just right, and some of them orbit stars remarkably similar to our own. One such system is TRAPPIST-1, a red dwarf star about 40 light-years away, hosting 7 Earth-sized planets, at least 3 of which lie within the habitable zone. These planets are so tightly packed that if you stood on one, you could see your neighboring planet hanging in the sky, larger than the Moon appears from Earth. Red dwarfs, like TRAPPIST-1, are smaller and cooler than the Sun, and much more common, making up about 75% of the stars in the Milky Way. This suggests that Earth-like planets could be far more abundant than once thought. Detecting an exoplanet is only the first step. The real challenge is determining its atmosphere and composition, and whether it might host life. This is where the James Webb Space Telescope, JWST, comes in. Launched in 2021, JWST has begun to study exoplanet atmospheres by capturing the faint light that filters through them as the planets pass in front of their stars. It can detect gases like water vapor, methane, carbon dioxide, and even signs of biological activity, known as biosignatures. Future missions like LUVOIR and HABEX may one day directly image Earth-like exoplanets, revealing their colors, clouds, and possibly surface features. If we find a world with oxygen, water, and methane coexisting in the atmosphere, it would strongly suggest biological processes, perhaps even life. At Infinity Beyond, we see each new exoplanet as a message in a bottle, a signal that the cosmos is teeming with possibilities. These distant worlds challenge our assumptions, expand our understanding of planetary diversity, and bring us closer to answering the age-old question, are we alone? The truth is, we've only just begun the search. With each passing year, our instruments grow sharper, our methods more refined, and our reach further. Somewhere out there, under the light of a distant sun, may lie another Earth, waiting to be found. The discovery of exoplanets has reshaped our view of the universe, revealing a galaxy brimming with strange and diverse worlds. But finding planets is only the beginning. At Infinity Beyond, we ask a deeper question, one that has echoed through millennia. Is there life out there? And if so, what might it look like? Here on Earth, life has proven astonishingly adaptable. It thrives in boiling volcanic vents, beneath Antarctic ice, and in toxic acid lakes. This wide tolerance suggests that life, at least in microbial form, could exist in a far broader range of environments than once thought. That idea has fueled the field of astrobiology, which seeks to understand not only where life might exist, but how we might recognize it when we see it. The basic requirements for life, as we know it, include liquid water, chemical energy, and organic molecules. These ingredients are surprisingly common throughout the universe. Water has been detected on moons like Europa and Enceladus, in the atmospheres of exoplanets, and even in interstellar clouds. Organic molecules, the building blocks of DNA and proteins, have been found on comets, in meteorites, and drifting in deep space. But what if alien life doesn't follow the blueprint of Earth? It's possible that life elsewhere could be based on different chemistries. Instead of carbon-based life that relies on water, alien organisms might use silicon, ammonia, or methane as their foundation. On Titan, Saturn's largest moon, surface lakes of liquid methane replace Earth's water oceans. Could some form of methane-based life thrive there, using a chemistry alien to everything we know? Mars rovers have begun to investigate surface clues that point to recent water activity. Dark streaks known as recurring slope linii, RSLs, have been observed on Martian hillsides, appearing and disappearing with the seasons. Initially thought to be caused by briny water flows, the current interpretation leans toward dry granular flows. But the debate is still ongoing. Regardless of their origin, the seasonal nature of these features hints at active processes occurring today on Mars. Furthermore, the detection of methane in Mars's atmosphere remains one of the most intriguing modern mysteries. Observations show that methane levels fluctuate with the seasons and even spike in localized areas. Because methane is destroyed by ultraviolet light within a few hundred years, its presence suggests a contemporary source, either geological or biological. If it's biological, even at a microbial level, it would mark one of the most significant discoveries in history. This is why missions like Perseverance and ExoMars are so vital. Equipped with instruments capable of detecting organic compounds and analyzing soil chemistry, they're searching for signs of past or present life in some of Mars's most promising locations. Meanwhile, orbital missions continue to scan the planet's crust, mapping subsurface anomalies and seeking out ice-rich regions that might one day support human explorers, or harbor something more ancient. At Infinity Beyond, we look at Mars as a world of potential just beneath the dust. A planet where ancient environments may have given way to hidden, enduring oases of warmth and chemistry. Mars might seem lifeless on the surface, but nature has shown us time and again that life finds shelter in the unlikeliest places. And if there is still life beneath the Martian surface, even microbial and unseen, then Mars is not just a fossil world. It is a living one, quietly enduring, waiting for us to discover its secrets. Mars is more than just the red planet. It is a canvas on which humanity projects its deepest hopes, fears, and questions about life, survival, and destiny. At Infinity Beyond, we see Mars not as a dead rock in space, but as the gateway to answering some of the most profound mysteries of the cosmos. So far, our robotic emissaries have uncovered evidence of an ancient world shaped by water, volcanic activity, and possibly a once-thriving atmosphere. We've seen clay-rich sediments, river deltas, and minerals that could only have formed in the presence of liquid water. We've measured methane plumes, examined ancient lake beds, and peered deep below the planet's icy crust with radar, all pointing toward a complex and dynamic history. Yet, for all that we've learned, the most important discoveries may still lie ahead. The Mars Sample Return Mission, a collaboration between NASA and the European Space Agency, aims to bring actual pieces of the red planet back to Earth for the first time in history. These carefully selected rock cores, gathered by the Perseverance rover, will undergo detailed analysis in Earth-based laboratories, with tools far more sensitive and accurate than anything we can currently send into space. If microbial biosignatures exist, fossilized or chemical, we may soon have the ability to confirm them beyond doubt. That confirmation would represent a watershed moment in science. It would prove that life can originate independently in multiple locations across the universe, strengthening the argument that life is common, not rare. The philosophical impact would be even greater. It would force us to reevaluate our place in the cosmos, not as the sole bearers of consciousness, but as one thread in a vast, interconnected tapestry of life spread across galaxies. But even if no evidence of life is found, Mars still holds immense value. Understanding how and why Mars changed from a habitable world to a frozen desert can teach us crucial lessons about Earth. It provides a real-world example of planetary climate change, atmospheric loss, and geological evolution. Mars reminds us that habitability is not a given. It is a temporary, delicate state, one that must be protected. The red planet also serves as a proving ground for future exploration. Every mission we send tests our ability to operate in extreme environments, develop autonomous technologies, and push the boundaries of engineering. Rovers, orbiters, and landers are more than scientific instruments. They are training wheels for eventual human presence. And make no mistake, humanity's future will include Mars. Whether it takes 10 years or 100, a human will one day step onto the Martian surface. That moment will be more than symbolic. It will be practical, emotional, and transformative. It will signal that life from Earth has extended its reach, that a new chapter in the human story has begun, not just on another planet, but in a new epoch of exploration. At Infinity Beyond, we believe Mars connects the past to the future. Its ancient rocks whisper of times long gone. Its modern mysteries provoke the minds of scientists and explorers. And its potential as a new frontier ignites the imagination of generations yet to come. So we continue the search. We launch new missions. We analyze every dust sample and photograph every crater. We listen for chemical whispers and read the stories etched in sediment. Because somewhere on that cold and dusty world may lie the greatest revelation of all. Not just about life elsewhere, but about ourselves. Leaving behind the dusty plains of Mars, we now set our sights on the true giants of the solar system. Worlds that are not made of rock, but of gas and ice, pressure and storms. At Infinity Beyond, we consider this the gateway to a vastly different chapter of planetary science. Welcome to the realm of Jupiter. Jupiter is not just the largest planet in our solar system, it's a planetary titan. With a diameter of over 142,000 kilometers, nearly 89,000 miles, it could fit more than 1,300 Earths inside it. But Jupiter's size is only part of what makes it fascinating. It is a planet of extremes, an alien world whose atmosphere churns with immense storms, whose magnetic field dwarfs that of all other planets, and whose family of moons includes some of the most promising places to search for life beyond Earth. From a distance, Jupiter dazzles with its bands of red, white, and ochre. These bands are massive belts of high-speed winds flowing in opposite directions, encircling the planet like ribbons of cosmic energy. Between them rage enormous storm systems, the most famous being the Great Red Spot, a swirling anticyclonic storm larger than the entire Earth, which has been raging for at least 400 years. Unlike the terrestrial planets, Jupiter has no solid surface. Its atmosphere deepens gradually into a supercritical fluid, neither liquid nor gas, under immense pressure and heat. Beneath that may lie a core of heavy elements, but even that remains uncertain. The deeper you go, the stranger it gets. Metallic hydrogen, electrical storms, crushing forces that science can barely replicate. Jupiter is also the solar system's protector. Its immense gravity serves as a gravitational shield, deflecting or capturing many comets and asteroids that might otherwise threaten Earth. This protective role may have been crucial in Earth's early history, allowing life to flourish in relative stability while Jupiter swept the solar system clean of dangerous debris. But perhaps the most intriguing aspect of Jupiter lies not in the planet itself, but in its moons. Jupiter is orbited by at least 95 known moons ranging from tiny, asteroid-like bodies to planet-sized spheres. 4 of them, the Galilean moons, Io, Europa, Ganymede, and Callisto, are worlds unto themselves, each with unique characteristics, mysteries, and potential for life. Among them, Europa has captivated scientists more than almost any other moon in the solar system. Europa is slightly smaller than our moon, but beneath its icy crust lies a vast global ocean, possibly containing twice as much water as all of Earth's oceans combined. At infinity beyond, we often refer to Europa as an ocean world, one of the most likely candidates for harboring extraterrestrial life, not on the surface, but in the dark, salty depths beneath its ice. In the coming years, NASA's Europa Clipper mission will embark on a detailed study of this enigmatic moon. It will orbit Jupiter and make dozens of flybys of Europa, scanning for signs of habitability, measuring its ice shell, magnetic field, and potential plumes of water erupting into space. These plumes could provide direct access to the ocean below, a rare opportunity to sample another world's subsurface ocean without drilling through kilometers of ice. Back on Jupiter itself, NASA's Juno spacecraft has been orbiting since 2016, collecting high-resolution data on Jupiter's gravity, magnetism, atmosphere, and auroras. Juno has already revealed that the planet's belts extend far deeper than previously thought, and that Jupiter's poles are home to swirling cyclones, unlike anything on Earth. At infinity beyond, Jupiter represents a threshold, a world that challenges our understanding of planetary formation, chemistry, and even biology. It is not a place we will ever walk upon, but it is a place that has shaped everything around it, and perhaps sheltered the very origins of life.
As Mercury's portrait continued to sharpen, thanks to the wealth of data from the Messenger mission, yet another layer of the planet's enigma was uncovered, its surprisingly active interior. Scientists had long assumed that such a small world so close to the Sun would have lost all its internal heat billions of years ago. Like Mars, Mercury should have cooled quickly, solidifying its core and ending any geological activity. But infinity beyond and planetary scientists across the globe were about to learn that Mercury had defied those expectations too. One of the most intriguing surprises was Mercury's magnetic field. Earth's magnetic field is generated by a dynamo effect. The movement of molten iron in its outer core produces electric currents, which generate magnetism. For Mercury to have a magnetic field, it must still possess a partially molten moving core. And indeed, Messenger confirmed this through careful measurements of gravitational and magnetic variations across the planet's surface. The results were astonishing. Mercury doesn't just have a core, it has a complex, multi-layered one. Beneath its solid silicate crust and mantle lies a solid shell of iron sulfide, which itself surrounds a liquid outer core and possibly even a solid inner core. This kind of internal structure was previously thought to exist only in much larger planets. That Mercury, the smallest rocky planet in the solar system, retains such an active and layered interior was a radical departure from expectations. The existence of a magnetic field was just one piece of the puzzle. Messenger also recorded its unusual shape. Unlike Earth's field, which is relatively centered, Mercury's magnetic field is offset, shifted significantly to the north. This lopsidedness remains poorly understood, but points to highly unusual and uneven convection within the core. It may also be tied to asymmetries in Mercury's crust and mantle, or residual effects from that ancient cataclysmic collision. What this revealed to scientists at Infinity Beyond is that Mercury is not a geologically dead world. Far from it. While it lacks the plate tectonics or eruptive volcanoes of Earth, the interior processes that power magnetic activity and possibly slow geological reshaping are still ongoing. This realization places Mercury in a unique position among the rocky planets, part relic of the past, part dynamic system. In tandem with this discovery was a deepening appreciation of how Mercury's layered structure might have formed. As the young solar system settled into its final arrangement, Mercury found itself subjected to incredible forces: collisions, solar radiation, tidal stress, and orbital perturbations. These forces not only altered its orbit, but also influenced how heat moved through its interior, possibly preserving a liquid layer longer than previously imagined. Understanding how Mercury's core remains molten despite its small size has led researchers to propose several theories. One posits that radioactive elements trapped deep within the planet during its formation continue to release heat. Another suggests that tidal flexing caused by its close orbit around the Sun contributes enough mechanical energy to keep parts of the core fluid. Either way, the presence of a functioning magnetic field and a layered interior makes Mercury one of the most unexpected members of the solar system's inner circle. At infinity beyond, Mercury's strange magnetism and enduring dynamism are reminders that our assumptions about planets, based on size, distance, or even past models, must always remain flexible in the face of new evidence. Mercury defies easy categorization. It's a planet that should be quiet, cold, and still, but instead it pulses with the legacy of a violent past and the whisper of ongoing internal power. Mercury's bizarre structure, its massive iron core, lopsided magnetic field, and unexpectedly dynamic interior can't be fully understood without examining the early environment in which it formed. About 4.5 billion years ago, the inner solar system was not the calm, orderly place we see today. It was a chaotic battlefield of planetary embryos, rocky debris, and competing gravitational forces. In this primordial arena, only a few worlds would emerge intact. Mercury was among the survivors, but not without paying a heavy price. The story begins in the protoplanetary disk, a swirling, dusty plain around the young sun where particles collided, clumped together, and gradually grew into full-fledged planets. At that time, space was thick with fragments of rock and metal, some no larger than grains of sand, others the size of small moons. These planetesimals repeatedly collided and merged, forming larger and larger bodies. But this process was anything but smooth. Mercury's formation was deeply entangled in this early violence. Scientists now believe that Mercury did not accrete smoothly from dust and rock like Earth. Instead, it likely endured at least one titanic collision, a catastrophic impact that not only shaped its orbit but stripped away much of its original outer layers. This collision may have blasted away Mercury's silicate mantle, leaving behind the iron-rich core we see today. In the wake of such a tremendous impact, the resulting debris would have been scattered into space or reaccreted onto other planets. Data from the Messenger mission and models examined by the Infinity Beyond team strongly support this scenario. The absence of a thick mantle and the planet's unusually high metal-to-silicate ratio are difficult to explain otherwise. This so-called mantle stripping hypothesis not only accounts for Mercury's enormous core, but also provides a compelling framework for understanding its unusual chemical composition. But this theory raises another question. What happened next? How did Mercury settle into its current orbit, the innermost of all planets? To answer that, we need to consider the gravitational influence of the solar system's biggest bully, Jupiter. During the early migration of the giant planets, Jupiter is thought to have moved inward from its original position before shifting back outward, a process known as the Grand Tack hypothesis. As it moved, Jupiter's immense gravity would have disrupted the orbits of the inner planets, scattering material and reshuffling the layout of the early solar system. Mercury, small and light compared to the growing gas giants, may have been caught in this gravitational turmoil. Flung inward by Jupiter's influence and destabilized by its earlier collisions, Mercury could have been pushed into its current sun-scorched orbit. Once there, it became locked in a precarious dance, spiraling around the sun on the most eccentric path of any planet, scorched on one side and frozen on the other. This tumultuous journey left Mercury permanently scarred, not only physically but dynamically. Its highly elliptical orbit causes intense solar heating on its perihelion side, while the lack of atmosphere allows temperatures to plummet dramatically during the long night. The The resulting stress on the planet's surface contributes to massive faults and escarpments, still visible today. At infinity beyond, the tale of Mercury is more than just a planetary origin story. It is a vivid reminder that the solar system we see now is the result of unimaginable destruction and randomness. Mercury is the battered core of a world that could have been very different, a world that perhaps once had oceans, an atmosphere, and the potential to support life. Instead, it was reshaped by cosmic violence into a metallic ember, circling the sun like a silent witness to the chaos of creation. Despite the overwhelming evidence of Venus's present-day hostility, the idea that this planet once had oceans and a temperate climate continues to gain traction. At infinity beyond, scientists and enthusiasts alike have become increasingly interested in reconstructing Venus's lost history, not as a science fiction fantasy, but as a data-driven scientific endeavor. With the help of computer simulations and comparative planetology, a growing body of research now paints a compelling picture of ancient Venus as a true water world. One of the most groundbreaking efforts to explore this idea came from a team at NASA's Goddard Institute for Space Studies, GISS. Using Earth-based climate models, modified for Venusian parameters, the team was able to simulate atmospheric behavior on a young Venus, assuming the presence of shallow oceans and an Earth-like atmosphere. The results were stunning. The model suggested that Venus could have sustained stable surface water for up to 2 billion years. Temperatures would have remained well within the range necessary for liquid water and perhaps even for life. Days on Venus, lasting over 200 Earth days due to its slow rotation, would have seen long sunrises and sunsets. But with an Earth-like atmosphere, the heat would have been managed through cloud formation and atmospheric circulation. One of the most interesting tweaks the GISS team applied to the model was the proportion of land versus ocean. When they increased the amount of dry land, especially in tropical regions, it dramatically reduced the evaporation rate from the oceans. This helped to prevent a runaway greenhouse effect, suggesting that even with a slow rotation, Venus could have avoided the disaster that eventually unfolded. From the perspective of infinity beyond, this is where the science becomes truly awe-inspiring. Imagine a Venus with rivers, lakes, and cloud-covered skies. The highlands we now see through radar, such as Ishtar Terra and Aphrodite Terra, could have been continents rising above shallow seas. The atmosphere would have been breathable, or at least far more benign than the crushing CO2-filled furnace it is today. It's entirely possible that this version of Venus lasted longer than life has existed on Earth. But, like a classical tragedy, Venus's tale turned dark. As the sun continued to brighten with age, a natural process for main sequence stars, Venus's oceans began to evaporate. More water vapor in the atmosphere led to a stronger greenhouse effect, creating a dangerous feedback loop. Eventually, the planet crossed a critical threshold, entering what scientists now call a runaway greenhouse state. Without oceans to trap and cycle carbon dioxide, atmospheric CO2 levels skyrocketed. Surface temperatures rose to extreme levels, and any remaining water was broken apart by solar radiation. Hydrogen escaped into space, while oxygen either bonded with surface minerals or was lost. Venus's skies thickened with clouds of sulfuric acid, and the planet became the hellscape we see today. And yet, the echoes of that lost world remain. Radar data from the Magellan mission in the 1990s helped generate a detailed topographic map of Venus, allowing scientists to reconstruct its ancient terrain. When water is digitally added to the lowest regions of this map, a striking possibility emerges: the outlines of ancient oceans, vast and blue, resting between the highland continents. For researchers at Infinity Beyond, this serves as a haunting reminder. Habitable conditions are not guaranteed to last forever. Planets can change, sometimes slowly, sometimes catastrophically. In Venus, we see not only a twin of Earth, but a shadow of what could have been or might yet be elsewhere in the cosmos. To understand why Venus transformed from a potential paradise to a scorched wasteland, we must look not just at the planet itself, but also at its central star, the Sun. At Infinity Beyond, we often remind our audience that no planet exists in isolation. The fate of a world is intricately tied to the life cycle of its star, and in the case of Venus, the aging Sun played a pivotal role in determining the planet's ultimate downfall. When the solar system was young, the Sun was significantly dimmer than it is today. This faint young Sun phase may seem counterintuitive, but it's a well-understood aspect of stellar evolution. Main sequence stars like our Sun gradually become brighter and hotter as they age. In fact, astronomers estimate that around 4 billion years ago, the Sun's luminosity was about 30% lower than it is now. This cooler state created ideal conditions for the inner planets, especially Earth and Venus, to host liquid water. On Earth, these conditions allowed early life to emerge in its oceans. On Venus, the same diminished solar output may have sustained shallow seas and a temperate climate. For hundreds of millions, perhaps even billions of years, Venus could have existed in a state not too different from Earth, basking in gentle sunlight with a stable atmosphere and hydrological cycle. But the clock was ticking. As the Sun continued to age, its brightness steadily increased. For Venus, slightly closer to the Sun than Earth, this change had profound consequences. More sunlight meant more energy striking the planet's surface, gradually increasing temperatures. This warming began to evaporate surface water, sending water vapor, an extremely potent greenhouse gas, into the atmosphere. The greenhouse effect is a natural process. It helps maintain habitable temperatures by trapping some of the heat radiated from a planet's surface. On Earth, this process keeps our average temperature at a life-sustaining level. But on Venus, the greenhouse effect spiraled out of control. As more water vapor entered the atmosphere, more heat was trapped, which caused even more water to evaporate, a runaway feedback loop. Eventually, Venus's oceans began to disappear into the sky, not as gentle clouds, but as superheated vapor. Ultraviolet radiation from the Sun broke apart water molecules, releasing hydrogen and oxygen. The light hydrogen atoms escaped into space, while oxygen reacted with surface rocks or was similarly lost. Without water to act as a carbon sink, carbon dioxide accumulated rapidly, amplifying the warming process. The result was a planet-wide transformation. What had once been a blue world turned into a superheated furnace. Surface temperatures soared past 460 degrees, and the atmosphere thickened into a blanket of carbon dioxide nearly 100 times denser than Earth's. Any remaining traces of life, if they had ever existed, would have been obliterated in this slow-motion planetary disaster. For researchers and storytellers at Infinity Beyond, Venus is not just a scientific curiosity, it is a profound warning. The runaway greenhouse effect that consumed Venus is a real physical process, one that can occur on any world under the right conditions. The frightening part is how subtle the tipping point may be. A planet may be perfectly habitable for billions of years, only to cross a threshold that sets it on an irreversible course toward destruction. That's why scientists study Venus so intensely, not only to understand its past, but to better protect our own planet's future. In many ways, Venus shows us the fragility of planetary habitability. The Goldilocks zone isn't simply about distance from a star, it's also about the balance between atmosphere, radiation, and chemistry. And as Venus teaches us, even a planet that starts in the right place can be lost if that balance is broken. The story of Venus serves not only as a record of planetary evolution, but also as a powerful allegory for what can happen when delicate atmospheric balances are lost. At Infinity Beyond, we view the case of Venus as one of the most striking natural experiments in the solar system, a sobering reflection of what awaits a planet when the greenhouse effect spirals unchecked. To fully appreciate the transformation of Venus, we must delve deeper into the physics behind the greenhouse effect. It begins with sunlight, primarily in the visible spectrum, penetrating a planet's atmosphere and reaching the surface. This solar energy heats the surface, which then re-radiates the energy as infrared radiation, essentially thermal energy. Here's the key. While the atmosphere is relatively transparent to visible light, it is far more opaque to infrared. Gases such as carbon dioxide, methane, and water vapor absorb this outgoing radiation, trapping heat and warming the planet. On Earth, this greenhouse effect is what keeps our average surface temperature around 15 degrees, and 59 degrees should I say, rather than the frigid 18 degrees it would be without it. But the same physical process that protects life can also destroy it. Venus is the perfect example of this extreme. Once Venus began to lose its surface water and increase its atmospheric water vapor content, the greenhouse effect amplified drastically as temperatures soared, all remaining liquid water vaporized. With no oceans left to act as a carbon sink, an essential regulator on Earth, the CO2 levels in the atmosphere ballooned. Eventually, carbon trapped in rocks was also released, further exacerbating the warming. The atmosphere thickened and grew increasingly opaque to infrared radiation, turning Venus into a heat trap from which there was no escape.
Today, the Venusian surface is an environment of unimaginable extremes. A pressure of 90 Earth atmospheres, temperatures nearing 470 degrees, 880 degrees, and clouds composed of concentrated sulfuric acid. No lander has lasted longer than a few hours under these conditions, and no known form of life could endure the conditions we find there today. But what truly unnerves scientists at Infinity Beyond is the realization that Venus's fate was not the result of any catastrophic external impact or celestial event. There was no asteroid that shattered its crust, no rogue star that stripped its atmosphere. The collapse happened slowly, inexorably, from within, driven by feedback loops in its own climate system. This recognition forces us to ask uncomfortable questions about Earth. Although our planet sits further from the Sun and benefits from a more favorable climate and atmospheric composition, we are not immune to the mechanisms that doomed Venus. Already, Earth's carbon dioxide levels have surpassed 420 parts per million, higher than at any point in the last 3 million years. Global temperatures are rising, glaciers are melting, and weather patterns are growing increasingly erratic. The fundamental physics are the same. The more greenhouse gases we pump into the atmosphere, the more infrared radiation becomes trapped, and the more our planet heats. The difference between a stable Earth and a runaway Venus-like climate is not as wide as we once believed. It is not an immediate threat, but it is a future that becomes more probable with inaction. At Infinity Beyond, we use Venus as a lens through which to view Earth's potential futures. Not because Earth will inevitably become like Venus, but because the parallels are scientifically valid. Venus reminds us that planetary habitability is not a guarantee. It's a tightrope walk, maintained by geology, atmosphere, oceans, and biology in a complex and delicate interplay. Understanding what went wrong on Venus might be the key to preventing it here. And perhaps, in studying that fiery world, we'll learn to better cherish and protect the fragile blue one we call home. Among the 4 rocky worlds in our solar system, Mercury, Venus, Earth, and Mars, only one has maintained the elusive balance necessary to support complex life. While Mercury was stripped and scorched, and Venus succumbed to a runaway greenhouse effect, Earth has remained uniquely stable for over 4 billion years. At Infinity Beyond, we often reflect on this improbable balance and what it tells us about the rarity, fragility, and wonder of our home planet. Earth's continued habitability is not a simple matter of location within the so-called Goldilocks zone. While distance from the Sun certainly plays a role in allowing for liquid water, the planet's long-term success hinges on a multitude of interconnected systems. These include its dynamic atmosphere, protective magnetic field, active plate tectonics, and, crucially, the presence of life itself. Each of these systems contributes to regulating temperature, recycling materials, and maintaining the delicate conditions that make our world not just livable, but thriving. Life plays a central role in maintaining this balance. Through the process of photosynthesis, plants and algae absorb carbon dioxide and release oxygen, reshaping the atmosphere over billions of years. The Earth's oceans act as vast carbon sinks, moderating climate by absorbing excess heat and CO2. Geological processes such as volcanism and weathering also help recycle nutrients and gases, further stabilizing atmospheric composition. But life is not just a passenger in Earth's story, it is a planetary force in its own right. The Gaia hypothesis, proposed in the 1970s by James Lovelock and Lynn Margulis, suggests that life and the planet co-evolve, with living organisms helping to regulate Earth's environment in ways that promote their own survival. Whether or not Gaia is a literal mechanism, the evidence is clear. Without the presence of life, Earth's climate would be radically different, and perhaps much less stable. We know this because we have the contrast of Venus and Mars. Mars, once potentially habitable, lost its atmosphere and surface water, likely due to its small size and lack of a protective magnetic field. Venus, for all its Earth-like beginnings, fell into climate catastrophe. Earth alone has walked the razor's edge of habitability, and for reasons we are still working to fully understand, it has not yet faltered. Yet this balance has been tested repeatedly. Earth has endured mass extinctions, asteroid impacts, supervolcanoes, and ice ages. And through it all, life has not only persisted, it has evolved into countless forms, adapting and surviving. From the simplest single-celled organisms to the complexity of human beings, life has become the most dominant and creative force on the planet. At infinity beyond, we see Earth not just as a planet, but as a dynamic biosphere, a self-regulating system where geology, climate, and biology interact in a continuous feedback loop. This understanding reshapes how we view other worlds. It forces us to ask, is life a fluke or a natural outcome given the right conditions? Can the fragile balance we see on Earth arise elsewhere? Or are we truly alone? These are not merely academic questions. As humanity begins to look outward, to Mars, to Europa, to distant exoplanets, we carry with us the lessons of our own planet. We have one proven example of a living world, and it is a world of remarkable resilience but undeniable vulnerability. In studying the fates of Mercury, Venus, and Mars, we come to appreciate that Earth's stability is not guaranteed. It is earned, maintained, and dependent on how we treat it moving forward. Venus shows us how a planet can burn. Mars shows us how a planet can freeze. Earth shows us what happens when everything goes just right, for now. As we leave the scorched landscapes of Venus and the delicate, life-sustaining balance of Earth, our attention turns to a world that seems both familiar and alien. Mars. Known for its rust-red hue and its prominent role in both science and science fiction, Mars is the fourth planet from the Sun, and the most Earth-like of all other worlds in our solar system. At infinity beyond, we see Mars not merely as a dusty desert, but as a time capsule, a planet that once may have looked remarkably like our own. Despite its current barren appearance, Mars offers countless clues that it was once a very different place. Satellite images and rover missions have revealed the unmistakable signs of ancient riverbeds, dried lake basins, and even delta formations. These features are not speculation. They are geological evidence of water's enduring presence on the surface of Mars billions of years ago. One of the first breakthroughs came from NASA's Viking orbiters in the late 1970s. They revealed vast channels that could only have been carved by flowing liquid. Later missions, particularly Mars Global Surveyor and Mars Reconnaissance Orbiter, added layers of high-resolution imagery, exposing complex networks of valleys and mineral compositions that form only in the presence of water. Then came the rovers. Spirit and Opportunity, twin explorers sent by NASA in 2004, drastically changed our understanding of Martian history. They found clear signs of past hydrothermal activity, water-altered rocks, and minerals like hematite and gypsum that could only form in wet conditions. Later, the Curiosity rover, still operating today, discovered evidence that Gale Crater once held a long-lasting freshwater lake. Organic molecules, the building blocks of life, were detected in the sediments. All of this data points to one astonishing conclusion. Mars was once warm and wet, with a climate potentially suitable for life. Around 3.5 to 4 billion years ago, the red planet may have had a thicker atmosphere, a stable water cycle, and even a magnetic field to shield it from solar radiation, conditions remarkably similar to early Earth. So, what happened? At Infinity Beyond, we explore the prevailing theory that Mars lost its magnetic field early in its history. Without this protection, the solar wind, a stream of charged particles from the Sun, began stripping away the planet's atmosphere. Over millions of years, the once thick air thinned to a whisper, and with it, the ability to retain heat and water vanished. Mars transitioned from a potentially habitable world to a frozen desert. Today, Mars's atmosphere is less than 1% the density of Earth's. Temperatures fluctuate wildly, from a high of 20 degrees, 68 degrees during the day, to lows of 100 degrees, 148 degrees at night. The water that remains is mostly locked in polar ice caps, or exists as traces of vapor and salty brine in the soil. The planet is dry, cold, and hostile, but not lifeless in its past. The importance of Mars lies not just in its potential for ancient life, but in its accessibility. Unlike Venus, Mars has a surface we can explore with rovers, landers, and eventually humans. It has seasons, weather patterns, and polar ice. For all its challenges, it remains our best chance at exploring what a second genesis of life might look like, or what happens when planetary protection fails. As we study Mars with increasing precision, from orbit and on the ground, we are slowly unraveling the mystery of a world that may once have teemed with life. And at Infinity Beyond, we believe Mars holds the keys not only to understanding the past, but also to shaping the future of human exploration.
As Mercury's dramatic story draws to a close, our attention shifts outward to a planet that, at first glance, should have been Earth's twin. Venus, nearly identical in size and mass to Earth, orbits just slightly closer to the Sun than our home planet. For centuries, astronomers assumed this similarity meant that Venus, like Earth, must be a living world. But as our exploration deepened, Venus proved to be a planet full of contradictions. Earth-like in form, but hellish in function. At Infinity Beyond, we often describe Venus as the ultimate cautionary tale of planetary evolution. What once might have been a temperate, water-rich world has now become a suffocating inferno. Surface temperatures exceed 460 degrees, 860 degrees Celsius, hot enough to melt lead, and the atmospheric pressure is 90 times greater than Earth's. This crushing environment is made even worse by an atmosphere composed almost entirely of carbon dioxide, cloaked in thick clouds of sulfuric acid. But Venus wasn't always like this. Climate models and planetary data suggest that billions of years ago, Venus may have had shallow oceans and an atmosphere much more like Earth's. These oceans could have persisted for up to 2 billion years. Ample time, theoretically, for life to emerge. The idea of a blue Venus is not science fiction. It's a hypothesis supported by data from multiple missions and advanced climate simulations conducted by NASA and other space agencies. In fact, data from the Pioneer Venus mission in the late 1970s provided one of the strongest pieces of circumstantial evidence for Venus's watery past. Instruments on board detected an unusually high ratio of deuterium to hydrogen in the Venusian atmosphere. Deuterium, a heavier isotope of hydrogen, tends to remain behind when water is lost through evaporation and atmospheric escape. The elevated ratio suggested that Venus once had vast quantities of water, possibly enough to form oceans. So what went wrong? The culprit appears to be the runaway greenhouse effect. As the young sun grew brighter over time, more solar energy reached Venus's surface. This caused increased evaporation of surface water, pumping large amounts of water vapor, a powerful greenhouse gas, into the atmosphere. The result was a feedback loop. Higher temperatures led to more water vapor, which trapped more heat, which led to even higher temperatures. Eventually, Venus's oceans boiled away. Without water to trap and sequester carbon dioxide, the gas built up unchecked in the atmosphere. Solar radiation broke apart the remaining water molecules, with hydrogen escaping into space and oxygen bonding with surface rocks or being lost. The planet's fate was sealed. At Infinity Beyond, we emphasize that Venus didn't fail because it was too small or too distant from the Sun. It failed because of how its atmosphere responded to gradual changes in solar energy. Its current state is the result of an environmental tipping point, one that may have begun slowly but accelerated beyond the point of no return. It is a stark warning to any planet with a fragile climate balance, including our own. Despite the harshness of its modern environment, Venus still holds clues to its past. Missions like Magellan used radar to penetrate the planet's thick cloud cover, revealing a surface shaped by volcanism, impact craters, and vast plains. Some scientists even believe Venus may still be geologically active today, with volcanoes quietly reshaping the planet's surface beneath its dense atmosphere. From oceans to inferno, Venus represents a path Earth could have taken, and still could if the balance of greenhouse gases tips too far. It is not just a failed twin, but a mirror through which we glimpse our own planet's possible fate. The mystery of Venus has haunted scientists for decades, not just because of its extreme conditions, but also due to how impenetrable it seemed for much of history. Unlike Mars or Mercury, which could be studied with direct imaging, Venus remained shrouded, both literally and figuratively. Its thick atmosphere of carbon dioxide, covered in dense clouds of sulfuric acid, reflects nearly 75% of the sunlight that hits it. Through even the most powerful telescopes, Venus appeared as nothing more than a bright, featureless orb. It wasn't until the second half of the 20th century that humanity began to peel back the veil. The Soviet Union led the charge with their ambitious Venera program, a series of increasingly complex spacecraft designed to do what no machine had ever done: survive on the surface of Venus. These missions were dangerous and technically daunting. Many of the early probes failed completely, either burning up during descent or being crushed by the immense atmospheric pressure. But perseverance paid off. In 1970, Venera 7 became the first spacecraft to make a successful soft landing on another planet. Though its parachute failed and it slammed hard into the Venusian surface, the probe managed to transmit temperature data for 23 minutes. This was a monumental achievement. Humanity had touched the surface of another planet and survived, if only briefly. The success of Venera 7 paved the way for even bolder missions. In 1975, Venera 9 not only landed successfully, but became the first spacecraft to return images from the surface of another planet. The black and white photographs it transmitted back to Earth showed a bleak and rocky landscape bathed in oppressive heat and pressure. It was a world more alien than anyone had imagined. Later missions pushed the boundaries even further. Venera 13 launched in 1981, functioned for 127 minutes on the surface, an impressive feat under conditions that included a temperature of 457 degrees C, 855 degrees F, and pressure equivalent to being 900 meters underwater on Earth. The spacecraft deployed spring-loaded arms to test the compressibility of the soil, drilled into the Venusian crust, to collect samples and even recorded audio of the wind on another world, a haunting, low-frequency hiss that seemed to whisper from a place that had once held promise. These missions, celebrated by researchers at Infinity Beyond, provided the most detailed and direct look at Venus's surface ever achieved. They confirmed beyond any doubt that the planet was not just inhospitable, but violently so. The terrain was jagged and fractured. The air was not only toxic, but corrosive. There was no trace of water, no signs of current life, and little hope that anything could endure such an environment. But the significance of these missions went beyond the data. They demonstrated what was technologically possible and set a precedent for pushing the limits of exploration. Venus, once thought to be a second Earth, was revealed as an apocalyptic warning, a vision of what happens when a planet's climate spirals out of control. At Infinity Beyond, the lessons of Venus are clear. This was a planet that had every reason to support life. Its early conditions, warmth, water, and Earth-like atmosphere, were the very ingredients of habitability. But through subtle and relentless feedback loops, Venus passed a tipping point. Its oceans vaporized, its skies thickened, and its surface turned from blue to burning. The planet we see today is the product of environmental collapse on a planetary scale. Even now, scientists continue to analyze radar data and atmospheric chemistry, searching for clues in the planet's distant past. Could Venus have once supported microbial life? Are there ancient fossilized biosignatures locked beneath its volcanic plains? These are questions future missions hope to answer.